So the way it works here, you need to determine the amount of strain that you have in the tensile steel. And once you have it, you go vertically with the line on the y-axis. You can figure out the stress reduction factor, the phi factor. It's gonna be that simple. We have here a good example, also taken from previous class, from the 408. They give here concrete section with a strength of the concrete 4,000 psi, and the yield strength is going to be 60,000 psi, which means grade 60 steel. And the question here, determine the capacity of this section, concrete section. So we don't have the beam span. You don't have the loading. We're just looking at the capacity of this section. So the way it works here, we're going to assume that we have a stress block. This is going to be weakness stress block with a maximum stress of 0.85 F prime C. So in this case, you take 0.85 times the 4K size, give you 3.4 K psi. The strain, because now this is going to be what we call here the capacity point. At the capacity point, the strain in the concrete at the failure of the capacity point is going to be 0.03. We understand that the code says at 0.03, concrete is going to be failing, but we know that concrete is going to be able to attain higher strain levels, but you need to leave some safety. So the code says only at 0.03, and beyond that, we're not going to be considering it. Now, the strain at the steel, at the bottom of the steel, is something that we don't know yet because we don't have this depth C of the neutral axis depth. Information given to us at the beginning was only the depth D, and the way that we figured it out, or it's given, that you have 16-inch total depth H. You have the cover, and then you have the tie, and then to the center of the rebar, you're going to end up with 13.5. And here's one line for the calculations of it. Total cross-section area, you have 3 number 8, and as I said before, do not try to do pi d square over 4. You just look it up from the steel table, reinforcing bar table, ASTM 615, and you have 3 times 0.79 for each rebar. We have 3 number 8. You have total of 2.37 square inches. So now I have AS, I have the depth, I have the width, but I don't have the compression block depth A. And this gives me the first point that I need to figure it out. Now, how do you do it? You set the tension equal to compression. And the questions give you now about the tension, how much tension force that you have in the rebars. Tension force is going to be equal to the cross-section area of all the steel, the 2.37. And yet, at this point, I don't know the exact strain in the steel and the stress. So I'm going to be assuming that the steel is yielding already, which is going to be usually my target, is to do a design in a way such that the steel is going to be yielding. So here's the first estimate. And this estimate needs to be confirmed later on. We assume here that the steel is yielding, meaning the stress is going to be at F sub Y. If the steel is yielding, the stress is going to be at F sub Y. And here, I'm going to set here tension equals compression. Tension is going to be AS times Fy, assumed. And the compression is going to be 0.85 F prime C times A times B. So we set them equal to each other, and my only unknown here in this case is going to be A, which is a compression block depth. This is going to be this value here. I set F sub Y equal to 60,000 psi, which means 60 KSI. And this is how I came up with the tension force. This tension AS times Fy is a tension force 142.2. How this is calculated out, it is by taking 2.37 multiplied by 60 KSI. With that, I have the compression block depth is going to be 4.18. And here we go. Now I have the compression block depth. Now, if you calculate out now the compression out of this equation is going to be the same as this tension force. They are equal to each other, which is good. I understand that. Now, I know neutral axis depth, which is this C, is going to be equal to this A divided by beta 1. So my next step is to solve for the neutral axis depth. Your beta 1 here, it is equal to 0.85. How do I know it? I have a chart for the beta 1. And this chart, it says beta 1 equals to 0.85 if the strength is going to be 4,000 or less. And for each 1,000 psi increase in the strength of the concrete, you're going to be reducing beta 1 by 0.05. So for example, if the concrete strength is 4,000, like in this case, beta 1 is 0.85. If the strength is 5,000, it's going to be 0.8 because we have a reduction of 0.05. So here we go. Now we calculate out the C neutral axis depth, 4.92. And based on these two triangles, now I have two identical or symmetrical triangles. Now from symmetry, I can say that 0.03 divided by 4.92 get you the slope of this line. It's going to be equal to the strain in the steel divided by the depth minus C, which means that this distance from here to there. It's exactly what we have in this equation. We determined that the strain in the steel is going to be 0.005 and the yield strain is 0.002. How do we come up with the yield strain? I say here E, which is ES equals Fy divided by, instead of epsilon, I'm going to be using E sub Y, the strain at the yield point. ES is 29,000 psi equals to 60 divided by the strain at the yield point. Therefore, EY, the strain at the yield point, is going to be equal to 0.0021, which is this value here. So what is this? This is going to be the yield point. It means my assumption turned to be correct. Someone's going to say, which assumption? I see this assumption here. I assumed that the strain in the steel is beyond the yield point, which means the steel rebar's intention is yielding. And it's true, I was able to confirm this. Now my next step is to go to this chart to figure out the phi factor. You see the strain in the steel is increasing in this direction. So I'm going to be at 0.0052. I'm going to be in this side, and my phi factor is going to be equal to 0.9. What's next is to find out Mn and phi min. Mn is going to be equal to the tension or compression multiplied by the distance from the tension to the centroid of the compression block. This here equals the depth D subtracting A over 2. I'm talking about this distance here, the arm. Sometimes you call it Z. You can say this Z here equals the depth minus A over 2, 1/2 of the depth. All right. Here is D minus A over 2, which is Z. 13.5 minus 2.09, A over 2. Multiplied by the tension force. And here we go. Here is, this is the moment capacity, nominal moment capacity in kip inch. Why kip inches? Because this force here in kips, and the dimensions here is going to be in inches. This is going to be kip inch. Usually we would like to see the moment at the end to be in kip foot, so I just need to divide this by 12. Now this is the nominal capacity. Multiplied by the phi factor. Here's the phi factor, the 0.5. We bring it down to 100 or to 121.7 kip foot. Any questions?
Excuse me, just wondering if in real life the strain rate for the series is the same as concrete, or we just assume that thing.
Say it again, the strain what?
The strain rate, how actually the steel strain versus how concrete strain. Because in this we should assume that they both strain with the same rate.
You mean the same rate, the slope of this line?
Yes, I think we use one chart or one profile for both concrete and steel. do we assume that they both have the same rate of straining?
So just to confirm, you're talking about this diagram, right?
Yes, strain profile. Yes.
Yeah, this one here. Yes,
Yes.
in practice, when you do an actual design, this is what you assume. And
So
part of our
that's
assumptions here that plane sections remain plane after bending,
okay.
which is not 100% true. So we have certain assumption here that comes with the design of concrete members, and this is gonna be one of them. Generally speaking, when you have a deep beam, I don't know if you hear about design and analysis of deep beams, when the beam becomes very deep compared to the width of it and compared to the span, this application here is not valid anymore. And in a case like this, you would use a stratum time model. So for
Thank you.
our analysis here, for reinforced concrete design, pre-stressed concrete design, we assume that the strain distribution is going to be linear, in linear relationship, like the way that you see it here.
Thank you.
No problem. Now, next, we're going to start here with the pre-stressed. So I have this slide set. Little bit about the history of pre-stress, when does it start, and this kind of things. Start a long time ago, as you see here, 1824, and then you have more information. So it goes back many years, but it was not as decent as what we have now, not that evolved. Now, this can be the Freycinet. This Freycinet system is very famous, and there's a company that carries this name now, Freycinet. This is like the end block or the anchorage zone. So just to have an idea here, that you're gonna put here some cables inside the concrete, or tendons. You may call it cables, you may call it tendons, and they are made of high strength material. So the strength of the cable itself is really high. It is not like 6 KSI. It goes easily to 200 KSI. So are using here superior materials. And also the concrete strength, you cannot use like 2000 or 2500 or 3000 or 4000. Minimum that you're going to start with in pre-stress is going to be 5000 PSI. So this is going to be like the starting point. Now you're going to put the cable through the concrete. And from the name here, we call pre-stress, which means that you're going to be applying some tension or some stressing to this cable or tendon. When you do this, the cable itself is going to be anchored to the concrete. What does it mean by anchored? Just imagine here in conventional reinforcing rebars, the anchorage is provided by just putting some hooks at the end of the rebar, like 90-degree hook or 180-degree hook, and that's it, you're done. But in here, 90-degree hook is not going to help you with the tendons or the cables. So you need to provide a kind of a system or an anchorage that you need to put here at the end of the cable. So this guy here, Freycinet, he invented this system, which is still used, but it is not, of course, as old as this now. It is more modern, and it has been evolved. Yeah, a second here. Palos Verdes, I'm sure that you guys, maybe you have driven there before, right? Are you aware of the place?
Yes.
All right.
By the
Have
beach.
you ever been to, there is a small museum. Have you ever seen it?
Is that like on the coast?
It is right on the beach.
Oh yeah.
Okay. I went there once, and here's what I have seen. This is like a pipeline, a piece of pipeline, and I've taken this picture myself. This is a pre-stressed pipeline. I was really happy when I have seen it. I mean, this is a real piece and from the past. So the way it works is you have these wooden pieces, and to keep it together, what they do here, they bring the spiral wire and just wrap it and apply some tension to it. So what does this wrapping do? It is providing compression on the pipe. So when you have internal pressure from the water, now the internal pressure wants to open it up, and what's resisting? You're going to say the spiral, the pressure that you're gaining from the spiral. And this is one of the means of pre-stressing that people has been using in the past. Same thing, it's a pipe. So you have a couple of pieces of pipes, and it is true. I mean, it is made out of a piece of wood. They put it together and then they wrap this around it. Same thing also with the old barrel. I mean, the old system here, that what they do here, they bring this steel collar or plate, if you like, and they put the barrel all together, and then they start to apply here tension to the collar. And this tension is going to be actually, once you apply tension on the collar itself, on the steel plate, this is going to be provided compression on it. So you see here what happened? This compression action, right, is because of the tension that you put on the collar. So when you fill this barrel here with any materials, any fluids, now the fluids wants to open the barrel out. And what's resisting is going to be the tension that you have applied on the collar. This is also pre-stressing. I'm going to show you here some videos.
Computers are used to.
Give me here a second. Does it right here? Do you guys hear?
The entire process of producing a pre-stressed
Yes.
unit.
Do you hear
and
the
a
comments? All right,
pre-stressing
very
plant.
good.
In this case, a double T. A double T is used primarily in parking structures, but can be used in virtually any type of building, including office buildings.
This is going to be one of the precasters. This is in the yard or the factory facility. And this is where they produce double T's and other members and other pieces. So I'd like just to show you here the short video
Industrial
so that to
buildings
understand
and
what's going on
schools,
there.
To name a few.
Double T's are kind of a unique product with having a capability of having a very long span. When you start talking long spans, you're talking 60 feet plus, and sometimes go as high as 120 feet.
The typical day of a pre-stressing plant usually starts very early in the morning. The product from the previous day's casting has cured by now, and the pieces need to be stripped from the form to get ready for today's casting. For any pre-stressing plant, it is very important to maintain a clean plant. Maintaining neatness is not only positive from an image standpoint, but also from a safety standpoint, since any debris that might be left over from the day before could create a tripping hazard or other safety problem. The first part of the process is setting up of the form. A thorough cleaning of the entire form is done with basic labor and appropriate cleaning equipment. Setting the side forms, or in the case of a typical double T, the forms may be fixed forms with an appropriate draft to allow for easy stripping. Once the bed is clean, it's ready for setting up today's cast. This particular bed is set up for 5 double T's,
30% of Americans
each about
are
60
getting
feet
almost
long. The bed has a total length of 400 feet. This is a self-stressing form, where the form itself is designed to take the total pre-stress force in compression, and also to handle the eccentricity of the strands. Sometimes
The strands is going to be the same as the tendons, same as the cables. So you can use any of these things. Now, what you're looking here at is pre-stress and precast. So the term here, precast, does it mean that there is some pre-stressing? In many cases, we have precast, but it is not pre-stressed. If this makes sense to you, meaning I can cast the concrete member like a box or a vault or maybe a beam, and this can be just cast at the facility, at the yard, but it doesn't have pre-stressing. Okay, like any conventional reinforced concrete section. This is what we call here precast. In our case here, we're looking at precast and pre-stress in the same time.
Producer may use a form that is set between bulkheads that are built right into the ground. The pre-stressing force is then resisted entirely by the bulkheads and their foundations. Next, the strands are placed in the form and extended from end to end. Crew members thread the strands through each of the dividers and then run them through the stressing plates at each end. The typical spacing of the strands is approximately 2 inches. This divider is a steel device that separates the individual double T units from one another. A gap of about a foot is typical between the ends of the adjacent pieces. This gap is required so the strands can be accessed and cut, and that each double T can be stripped from the forms. The next step is the tensioning of the strands. In this case, we have a strand pattern with straight strands of 6 strands.
So now the strands is coming out of the form from one end, and this is what you call here the anchorage pieces. Because now you are going to be anchored from one side, and you're going to go to the other side, and you start to apply tension on the strand. So this is the anchorage piece.
Strands in each stem, as shown here. The strands are first tensioned to about 2 to 5 kips based on the gauge pressure reading. In this case, a mark is made on the strand after the preload is applied. The strand is then tensioned to the specified level and is measured using the gauge pressure on the hydraulic pump. The QC technician then checks the elongation against the theoretical elongation. The requirement that is the force on the gauge and the elongation must match within 5%. If that tolerance is not achieved, the reason must be established and the strand may have to be detensioned and retensioned.
Just to clarify, this is a jack. This is what's putting tension on the cable. So on one side, you have all of this anchorage pieces, which means the other side of the form. And as they say here, the form is really long. He's talking about here 400 hertz.
Tension. After the strands of this double T are all stressed, the remaining embeds are set in place. These include stem reinforcing, lifting devices that will be used to strip and handle the piece, forms for blockouts in the flange, and forms for blockouts in the stems, flange reinforcing, and flange connectors or vectors along the edges. In this case, one of the double T's in the bed has typical flange connectors applied along one edge and special flat plate connectors applied along the other edge to accommodate connections across an expansion joint. The form is now ready to have concrete poured, but only after a pre-pour quality control check has been made and the QC person signs off on it. This QC check can also be done by the bed superintendent and depends on the particular plant's practices. Either way, the check is critical to ensure an end product with the highest quality.
There's all these things you look for, the mesh, you look for anything that could be touching the stems on the bottom, like wire ties that might have fell in there, because that would develop some type of rufus. You check the length, you want to make sure that the gaps are correct. Do we have the strand stripped properly? So there are a lot of critical areas that you need to verify.
Concrete is mixed at the batch plant under tightly controlled conditions. The cement is supplied using tanker trucks. Here, the cement is being blown from the tanker through piping to the cement silos. When needed, aggregates are delivered to bins in the batch plant. The aggregates are stored outside of the batch plant in separate bins. In this case, an enclosed vertical bin system is utilized. During winter, in northern climates, the aggregates must be heated to get them to flow properly through the batching system and to maintain proper concrete mix temperatures. Payloaders are used to shuffle the materials to the conveyor belt. Computers are used to proportion the materials for the desired concrete mix. Cement, sand, stone, water, and admixtures are measured according to signals from the computer. The materials
Right.
charged into a delivery device. It's imperative that the concrete mix be delivered to the form as soon as possible. These vehicles are called tuckers, and they are used to deliver the concrete to the bed in the yard. A self-consolidating concrete is being used to cast these particular double T's. With this type of concrete, vibration is not required to consolidate the concrete. However, minor controlled vibration is used in the double T stems to help remove air from the sides of the form, reducing bug holes in the stems. There are many advantages in using this type of concrete.
We do use self-consolidating concrete for our double T's. We feel that it gives us a better finish. We feel that it's easier to place, takes less labor, less strain on the labor to place that concrete.
The QC department will make the necessary tests at this time, including a temperature check of the concrete. Since SCC is being used here, a spread test is done to check the concrete flow in lieu of a slump test. The spread is measured to assure conformance to the planned spread. The edges of the circle of concrete are also inspected to check for segregation. The appearance is translated to a visual stability index number. There is a check for air content. Cylinders are filled and will be used later for strength tests of the cured concrete. Back at the bed, the concrete placement continues. A vibrating screed is used to level the surface evenly. A bull float is used to finish the surface. An evaporation reducing spray is also being applied to the.
Now I have a question for you. You guys recall the sequence? Construction, was that made on the site or at the facility? At the fabricator's facility?
The facility.
Yeah, this is like in the factory, right? All right. Did we do the pre-stressing first? Or did you do casting of the concrete first?
Pre-stressing first.
So pre-stressing first. So I guess we call this pre-stressed, correct?
Right.
And then we apply the tension first. So we call this pre-tension. Is there a difference between pre-stress and pre-tension? You say, well, pre-stress is like the whole thing. If you take any concrete member and you put strength and you apply tension to it and you anchor it to the concrete, we call this pre-stressed. Now, if you apply the tension before you cast the concrete, we call this pre-tension. If you apply the tension after you cast the concrete, we call this post-tension. Post-tension is also pre-stressed. So pre-stressed means, or it could be pre-tension or post-tension. So again, post-tension and pre-tension, both of them, you may consider to be pre-stressed. So again, difference between pre-tension and post-tension. Pre-tension, usually it is made in the factory, in the precaster yard. Post-tension, usually it is made at the site. If you do the work casting the concrete at the facility or at the factory of the precaster, we call this precast. If you do the concrete at the site where you're going to put the building or the bridge, we call this cast in place. Sometimes they refer to it as CIP, cast in place concrete. So you have here two methods of doing the concrete. Concrete can be done at the fabricator's yard or at the site. If you do it at the site, we call it cast in place. If you do it at the fabricator's place or factory, you call it precast. This means I can have cast in place concrete, and this cast in place concrete can be pre-stressed or conventional concrete with regular reinforcing. And also, if I'm doing it at the fabricator's yard, I can have precast, and this precast can be pre-stressed or conventional concrete. So any combination is okay. You can have pre-stressed and you can cast in the yard, or you can cast in the site. It's gonna be okay. Also, again, you may have cast in place and you can have it pre-stressed, or you can have it conventional reinforcing concrete.
Surface to minimize the potential for plastic shrinkage cracking. The final finish will vary depending on the use of the double T. If a cast-in-place topping is necessary, the surface will be made very rough so that a good bond will be achieved. If it is a roof, the finish will be relatively smooth, but not necessarily perfect. In this case, the surface is broomed as these double Ts are being used in a parking structure. Different patterns can be applied depending on the needs of the project. The bed is now in its curing stage. Sometimes, particularly in cold climates, the double T may be covered with tarps. In other areas, they may be open.
This is a good size
Accelerated curing
tarp.
is often done using live steam or radiant heat from heaters attached to the form itself.
Double Ts for parking garages really need to be held to a high standard. When they're assembled in a garage, they make the finished surface. There are tolerances for putting these pieces together, offsets in the surfaces. All of the connections are very sensitive as well. To be executed properly, the embedments in the double T have to be placed properly. So there, again, are a lot of critical issues that you have to be concerned with to get proper performance out of that simple double T.
After 12 to 16 hours of curing, the Ts are ready to be stripped. The QC department first tests the concrete to be sure it has achieved the strength required to detension the strands, typically 3,500 PSI. This is a typical test being conducted.
You say detention the strength. Did you guys hear that? So what does it mean? Now the strands, they are under tension. And the tension force goes to the form, goes to the end of the bed. At each end of the bed, the concrete bed or the formwork, you have two strong abutments. At each end of these, the strand itself is anchored to it. Correct? So the strand now is anchored to the abutment of the bed. Let me look here for a picture to show to you. I'm gonna go here to our slide set. I'm gonna say it is like this. This is gonna be like in the pre-tension. This is exactly what we were looking at. So first you have this abutment, and then you put the strands, and then you put tension to it. Now you put the concrete, you cast the concrete. So now the cable is under tension, and here's the concrete piece, the concrete beam or double T or whatever. And then after that, you're going to do here the detention. The detention means that you're going to be cutting the strands here from both sides. Now what's going to happen? The force that used to go to the abutment now is released. Now it's going to the concrete, and the concrete is going to start to camber. Does this make sense to you? Because now you start to put compression on the concrete. When you have tension on the rebars, it means that you put compression on the concrete. So let me continue here, and then we'll go back to our slide set.
The strands are detensioned in a specific
How does he
sequence
cut it?
established by the QC
He just
department
deburned it.
or the plant engineer. Here, personnel are positioned at each end of the bed and at some of the intermediate bulkhead locations. On a signal, they burn the strand at each end. After all the strands are cut and block-out formwork has been removed, the Ts are stripped from the form. Cables are attached to the lifting devices, and each piece is removed and transported to a detailing area for any minor cosmetic touch-ups. Also at this time, the QC department does a post-pour QC check on each piece that is brought to the detailing area.
When I first get back there, I go and check the length of the piece, verify that within, there's a tolerance of probably a quarter inch or so. Check the width, we check the vectors, we check the electrical blockouts. I do a visual for any type of discoloration in the stems underneath the piece, any type of surface cracks, bug holes, just do a complete visual.
Any defects are noted so that repairs can be done before shipping the tee. After all the work is completed, the double tees are moved into the storage area where they are typically stacked using appropriate dunnage located near the ends. When the job site requires the tee to be shipped, it is loaded on a trailer and transported to the job site. What you have just observed is the process for making one type of pre-stressed product. These other types are made using essentially the same process. Hollow core plank, which are used for floor and roof components in multifamily housing, schools, hotels, and many other buildings. Inverted T-beams, which can be used in any total precast concrete build system. Columns, which are cast horizontally and then rotated in the air at the job site. They are often designed as pre-stressed components. Architectural spandrels used in office buildings and parking structures can be made using the pre-stressing process. Deck slabs and box beams are also used in
These are like bridge beams.
Span bridge construction. Standard bulb tees are also used in long span bridge construction. Pre-stressed piles that support any type of building in areas that have unfavorable soil conditions. As you can see, there are many types of pre-stressed products available. The variety of products that can be pre-stressed in a long line operation is almost unlimited and is up to the imagination of the design.
Just want to take you here for 1 second, and I want to let you know that this green coating that you have on the rebars, this is epoxy. So this is actually the epoxy coated rebars. Next
line operation is almost
pictures. This is going to be conventional. This is not coated with epoxy.
We really do encourage our customers and architects and engineers to get to our plants to really understand how precast concrete is made. They need an understanding of the high quality that they can get out of precast concrete, as opposed to the random quality that you might get out of cast in place concrete.
Well, it's important that we do things as efficiently as we can and as cost effectively as we can, but also as well as we can. And it's not only my responsibility, but the responsibility of everybody here, management, labor, everybody included, to do the best job that they can to, at the end of the day, make a little bit of money, but also have a customer that's very happy.
All right, any comments or any questions? In the fabricator's yard thing. No comments?
I just had one. So since at the precast yard, obviously you could be very precise and have like quality control and all the time in the world.
Yeah, quality control, this is correct.
So to get around that, performance-wise, they do like a cost-benefit analysis and be like, in the field, obviously we can't be as precise, so we just make things a little bit bigger and stronger to kind of cover ourselves in that regard.
Yeah, usually it depends on the stands and the occupancy that you're gonna do for your building.
Yeah.
For example, if I'm looking here for, let's say, residential building or an office building, right?
Mm-hmm.
If you do office building and you think about doing it out of precast, it's gonna be really expensive because you don't need a span of 60 feet. But when you look here at the double T span, it goes up to 60 feet easily. So usually it's between 40 to 60 feet. But in an office building, you can put a column at, let's say, 30 feet, 28 feet on center, right? And most likely, if you do an office, it's gonna be structured steel so that you can build it fast and quick. And also the material is gonna be good. I mean, it's controlled. And the foundation size is gonna be manageable. But if you go to precast, it means that you're looking for real larger span. And the structure itself is gonna be a little bit heavier. And you need to end up with either concrete mount frames for the seismic or shear walls. Now, when you go with steel construction, you're gonna have a smaller spans, lighter building, a smaller foundation. So it depends on the span. I mean,
Okay.
Precast is perfect. You can use it for parking structures, bridges, usually parking structures and bridges. There is some precast members like the hollow core slab. You can use it in a small house if you want to. I have seen lots of people who just buy it and use it on the top of their garages, especially when the garage is kind of, let's say, subterranean, like in a basement or partial basement. A very good option here that you just bring some blanks, or you bring this what you call here the hollow core slab and just put on the top. And they're not that expensive. I'm gonna show also a video on the use of it. So what I was talking about here is the hollow core. I'm gonna show it to you, and you can cut it, you can trim it. It's very interesting the way it works. And the good thing, you can buy it for any residential building. If you have a small one, it's not that expensive. You see, we can saw cut it. And it has some strands inside. You see these dots here? These are like cables or strands, the tendons. And you can just cut it. You can trim it to the size you want it. Just want to show you here for quick, so I'm gonna be running it. And you understand this water is to cool down the blade, nothing for the concrete itself. Otherwise, you can burn the saw blade. And you see here the jet of water directly to the blade. Almost done. This is a very important bridge, and as you see here, here's the information of this bridge, and it was recipient of one of the awards. And you have really, I mean, when you look at this is one of the first precast bridges. You have this precast girders, and it is kind of neat. This is very standard for the whole core, which is the slab system. This is very good when it comes to small span. So you're talking here about, let's say, 10 foot, 20, 30 feet span. I would go with this. You don't go with the double T. So in many cases in the same building, let's say that you have reinforced concrete and then you have precast, pre-stressed building. In a case like this, not all the spans is gonna be like 60 feet and above, or let's say 50 to 60. Many spans is gonna be within, let's say, 20 feet. Whenever that you have is like a stair, or you have elevator core or whatever, right? So in a case like this, you need to have a small spans. And this hollow core section is gonna be very effective. As you see here in this picture, you have the precast columns, and it has a small corbel, one on each side, and then you have a beam that goes, it sits on it. Then you have the double T's, or the whole core is gonna be running across like a joist. This building here is like this, what you call here tunnel form. I don't know if you guys heard about this term before, the tunnel form construction. As you see here, the walls and the entire thing is made out of concrete. So it is going to be a different system here. So all of these walls and all the slabs, they come as pieces, and they have the big crane is going to be just assemble it, right? And certain sections, they're going to be made like cast in place, especially the connections between the walls and the slab. This is from a parking structure. And as you see here, you have the double T. This is the double T that you're looking at. So you have one double T. It's going to have two stems or two whips, another one, and they just put it next to each other. The inverted T beam that you're looking at in the video, here we go, here it is. It has a ledger. So it has a ledge, one ledge from each side of the beam. So the double T is going to come and sit on it. So here's the support for the double T. And this inverted T beam is going to be sitting on this corbel of the concrete column. So here's the concrete column, and you have this bracket or corbel, and then you have the beam sitting on it, and then you put the double T in the top to be supported by this inverted T-beam. Now, the big question is, what's going to be holding all of this together if you have an earthquake? And the answer to this, usually, we come here in the top of the double T, and then we pour a diaphragm. So we put first some reinforcing in the top of the double T, and then we pour 3-inch diaphragm. It's going to be concrete strength. It's going to be maybe 3,000, 4,000, and this is going to be holding the entire structure all together. The edge beam here, usually it comes with the guard drain. So we call it spandrel beam. So this is what you call here spandrel beam. So the spandrel beam here, it works as, if you like to call this a parapet or guard drain, at the same time supports the double T's. One of the famous structures, this is here a parking structure, and it is made out of mount frames. So you have here some mount frames. And look, you can slope it. Look at the slope when you have a ramp. So it is so easy when you slope it this way. If you just imagine that you build this out of reinforced concrete, like conventional reinforced concrete, it's going to be a really tough job, especially when you have the ramps. Ramp is going to be a big issue for the formwork and the reinforcing bars. But in here, it's going to be much easier because this column here, it comes with all the corbels right at the exact height that you want it to. And also the beams, it comes in the exact length. And of course, you're going to have some clearance right and left. Look here at this project. In the top, you have this double T's. This is what I was talking about. You have here a good span, and the double T is supported by, from one side by the wall, other side is going to be by this inverted T. But we come here at the first floor, and then all of a sudden they allow us to use central support. So now the span has been cut into 2 pieces. Instead of having, let's say, 50 feet or 60 feet, now you have 30 and 30. In a case like this, you don't want to use double T because double T is going to be really deep. The depth of the double T, total depth, is about 24 inches. It's kind of a standard of industry that use here 24 inches. For the hollow core here, this goes like 6 inch. You start at 6 inch, 8 inches, 9 inches, 12 inch, and you can easily span for 20 or 30 feet with this hollow core. And so the depth and the overhead is going to be much easier to maintain. And also the cost is going to be much less than the double T. Here's the way that you carry the double T, then they put it in place. You see here that you have anchors. You have 2 on each side, and each one of them is going to be connected to the stem or to the web. And as you see here, here's the hook. They carry it to the big crane, and then they put it in place. And if you see here, this notch that you have in the double T, some double T's, they come with notches. Some of them just come straight flat. It depends on the way that you're going to be supporting it. And this method here depends on the company. Each fabricator, they have their own standards. You're not going to see the same fabricator is going to give you a double T with a notch and also double T without a notch. We have certain hangers that they attach to the end. So the people or precasters who would produce a flat or a straight end of the double T, they have a kind of a hanger here in the top. Like this company is called Spankery. But other companies, they come here and then they do a notch. Notch is kind of, there's a little bit of more safety and easy of installation. But the other one, it's kind of easier in the yard. And there's little, I'm gonna say here, I don't wanna say dangerous, but there's little uncertainty when it comes to the installation and the hangers. You really need to be careful when you are using hangers, like the way the Spancrete would do. Look at this, this is gonna be the straight one. You can either sit on a ledge or you're gonna have a hanger. So in this case, you have a straight end of the double T and you just let it sit on the ledge. One of the methods that they do. This is the tallest reinforced concrete building on the West Coast. And the problem is the seismicity. You are here in high seismic zone. And this here is 39 story. Actually, it's 40. I don't know why they call it 39. This project here, it was designed between the year 99, and 2001. And there is no reinforced concrete shear walls. It is a system called hybrid moment frame. So the hybrid moment frame, they are pre-stressed moment frames. Code does not recognize this system. That was an invention at the time. That was something brand new. It was all new ideas. All the concrete slabs, they are all pre-stressed. This is a third dimension, but it has different name now. It is intersection equal Paramount Building, but this is intersection of 3rd Street and Mission Street in San Francisco. Here is the building itself. This is a floor plan, and as you see here, the grid lines. This for one of the typical levels that we made it as pre-stressed. I was lucky that I worked in this building, on the design of this building, and I spent at least 4 months just working on the PT slabs. All of the slabs here, they are all PT, like post-tension slabs. They're cast in place, and then after that, they applied the tension to it. And the slab thickness here was 8 inch. All levels, it was 8 inch thick slab. If you like to go with conventional reinforced concrete, you'd go to 10.5 and 12 inch slab. So I spent at least 4 months just working on the slab design. Now, the mount frames, they happen at each one of this side. You see this, this arrow here and this arrow. You have here one mount frame, another mount frame here, another mount frame here, one here and one here. And the method is called hybrid system mount frame. Very interesting project. And this is actually, it was to an award from the PCI. And I was really happy to work on this. That was a very important project to me at the time. Now, please members. Yes.
What makes it hybrid? The fact that they're like asymmetrical, or they're different size moment frames?
No, the hybrid, because it includes PT, like cables, big PT cable right in the middle of it, and also includes something called the WDAC connectors at the end. Maybe later on I can maybe share in some of the pictures and some of the details, original details. This is taken here from the original plan, as you see here.
Yeah.
It's from the original CAD file, and then I have all the grid lines, right?
Mm-hmm.
But the system here for the mount frame, it's kind of, I mean, it was not recognized by code. It was an invention by the person who owns the company that I used to work for. His name is Engelkirk, Professor Engelkirk. I don't know if you hear about it or not, but in San Diego, he has a lab that carries his name. It's called Engelkirk Center.
Nice.
At UCSD. Cool. He's a very famous person. So some of the sections that we use here in pre-stressing, like the double T's, and as I told you here, usually are going to have a topping, like concrete topping. So this shading is for some concrete topping that we put on the top, and this is going to be acting as our diaphragm when it comes to seismic. And the standard depth usually for this type of things is going to be 24 inch for the double T's. The width here ranges from 8 feet. There's some 9 feet. There's 12 feet, 10 feet, depends. There is also solid flat slab. You just buy it like this. It's going to be 4 inch. It's going to have some strengths. And look at this. Do you hear the concrete strength? And FP, which means like the strength. We're thinking here about 6 KSI. Here we are talking about 270 for the ultimate strength of this type of rebars or strengths. This is here the hollow core. It's very efficient. It is very light because it has this empty, you know, this is here is gonna be empty, like tubes. They made it out of cardboard. Sometimes they made it out of very thin, like gauge, like steel gauge. Most likely it's gonna be like cardboard, and the cardboard you can just pull it out after they are done. And here are the strands. Look at the strands. It's gonna be this dark dots. And here the strands are not shown, but usually you're gonna have 2 to 3, but most likely it's gonna be just 2 strands at the whip here. We have also some rectangular beams, not very common. Most likely it's gonna have a ledge. This is a beam that you're gonna see. Because if you're going to put this beam here, you need to put notches if you're planning to use the double T's with it, like in a Spancrete system. Spancrete is a fabricator name. But usually you'd like to use beams with ledge. So this ledge here, you're going to have the double T is going to come and sit on it. And this H1 is going to be your 24-inch, unless you're going to provide a notch in the double T. So in some cases, we put the double T like this. Double T is going to come like this. And the notch is going to be like this. So it comes and just sits in it. So sometimes you have a ledger beam and it's going to be only from one side. Sometimes you have it from both sides. So this is good here as a central support if you have double T's, one on each side. And this one here, if you just have it from one side and the other side is going to be open. And in a case like this, as you see here, that we don't have a parapet, which means a spandrel, right? So in some cases it comes without it. And in a case like this, they don't use this, and instead they use cables. It's going to be tension cables. Use like a cable at 4-inch on center. For at least it's going to be 30 inches. Right. We have also the sheet piles. This is different from the piles. So you have pile sections. You can have a rectangular section like this, or you can have round sections. You can have also columns, and you can have this sheet pile. Sheet pile is used for earth shoring. So let's say that you'd like to build a coffer dam, and coffer dam means this is when you are doing a good sized bridge, and you have the support of the bridge or the abutment that comes in the middle of a river. Or let's say it goes to somewhere in the ocean. Now you'd like to cast concrete, so you want to go at the bottom of it and do your business and your work, and you cannot. So what you need to do, you need to put a kind of a wall. So you're going to be hammering a wall like this sheet pile thing, and you're going to put a piece under, and then another piece next to it, another piece next to it, and you're going to be hammering it down, right, in the soil. And this sheet pile here can provide air shoring or water shoring. It can work as a water support if you're in the middle of a river. And once you build this coffer dam, which means this, I'm going to say here, it looks like a curtain, if you like to call it like a curtain, and then you can suck all the water, you can pump all the water out, and then you can pour the concrete inside if you want to. Now, when it comes to size and member size, this beam depth edge, it is a variable, but you have some standard size. It's going to be very similar to the structural steel beams. For example, in structural steel beams, we have, let's say, W12. What does it mean by W12? The depth is going to be 12-inch. Pi, and then you have the weight. We have also 16, we have 21. Same thing here. Same thing also for this double T. Some double T's, you go to 20 inches only. And then the size can be different. 8 feet, 10 feet, there's 9 feet, there's 12 feet, 10 feet, and so forth. So when it comes to the size of beams, we have some standard size, and then you need to pick one of them. You don't want to create your own new size, unlike conventional concrete. Otherwise, it's going to be very expensive. And most likely, you're not going to see anyone who's doing it for you. Also, you need to understand that the precaster or the fabricator, when you buy double T, this double T has been sitting there in the factory for at least like a year, maybe a year and a half. Otherwise, you're not going to find any precast members. This is what you need to understand, that you need to pick a size that's going to be available to you in the stock. Don't try to pick a size that you don't have it, there. Because who's going to do the form for you? Developing the form and the cost of putting the form all together is going to be very expensive. This form is used hundreds of times, and they keep on using it. And as you see here, they paint it with some oil, they call it form release, and then after that, they strip the double T, they just pull it up, and then they repeat the process. So don't go to weird size or your own size. Stay with the standard size. Now, where do you find the standard size? If you open the PCI. Are you guys familiar with the PCI document? The book? Yes? No?
No.
It is one of the books that I put in the syllabus, and I put in the first Let me look for something for quick.
Is it the one that we used in concrete class?
Here are some pages out of it. Here's one of the standard size that we use, 24" by 10 feet, right? So the depth is 24" and the width is gonna be 10 feet. And then you have different standard pattern when it comes to the cabling, the strands. And for each one of them, you have the span and then you have the allowed load. So actually you can use this. You don't really need to have a software. You can just pick the span, look at the load, and then see exactly which strand pattern that you're gonna be taking. And for this one, this is gonna be double T. And as you see here, it says here load table, and it shows you here how many strands. Out of this, you can figure out how many strands and the depth of the strands. And then you have also decision properties. So you have here 24". We call this 10 feet by 24" is gonna be normal weight concrete. Look at this, 8 feet by 32. So you have different size. So now I'm doing my design. Before even I start to look at one of these books, because this book here is kind of a standard for the entire industry, I would first talk to the precaster. You're gonna give him a call and then ask him what double T's are available. What is available in your yard these days or in your warehouse? How about the columns? Columns most likely is gonna be prepared for you. Why? Because the story height is gonna be different from a project to another project. The corbel design is gonna be different. But double T's, you need to have it in stock. The hollow core, you need also to have it in stock. The only thing that they're gonna build it especially for you is gonna be the column. Beams most likely is gonna be in stock, unless you come up with a special beam. When it comes to the span and number of strands, they can do it especially for you. And then you need to wait at least 3-4 months before you have it. So it is not gonna be like, let's order it, I'm gonna have it right now. The stuff that you have in the stock, like double T's, this is easy, you're gonna find it. Beams and columns, maybe you need to wait a little bit for it. So here's the method of pre-stressing. Let's see what is that about.
Small businesses.
Oh, that was a saw cutting. So here's what happened. This here what we call pre-tensioning, because in method of pre-stressing, we have two methods. One of them is called pre-tension, pre-stress concrete, and the other one is gonna be post-tension. If I may go here, this is gonna be post-tension. Now let's try to understand the difference, major difference between the pre-tension and the post-tension. Here's a pre-tension. This is very similar to what you have seen in the video. First, you have the abutments. You build the form or the bed, and then you run the strands, and then you apply the tension from one side, and the other side you're gonna have the anchorage. That's what you have seen, right? So what do you do after this? You cast the concrete. You put all the concrete in here. And then after that, you cut the strands from both sides. Otherwise, how would you take this out? I'd like to take this out, right? Once it reaches certain concrete strength, and as I say in the video, about maybe 3,500 psi, at that point, they should be able to carry it up. Now, this is here under tension. And this strand here is also under tension. When you cast the concrete, this concrete here is not stressed yet. Why? Because the tension goes to the abutment. So this rebar here, or the strand, is kind of stretched. You increase the length of it. When you apply tension to it, the length got increased by, let's say, the original length was L. Now we are adding delta L to it. So now it has some tension in there. All right, thank you, Desire. Desire had just sent everybody an attachment. It is the handbook, the PCI handbook. So it's good, now you have it. Now, once you cut the strands here from both sides, what's going to happen? It wants to go back to the original length, right? Now it was stretched already. Once you cut it, it wants to get short again. What's stopping it? What's stopping is going to be the bond between the strand and between the concrete. So just imagine, now you apply tension, now this tension is gone, as if you start with here some compression on the concrete itself. So this here represents a point load from both sides of the concrete beam. Once you do this, and the strand is going to be towards the bottom of the bed, now the concrete wants to go up. This means here you're going to have compression, and on the top you're going to have tension. So here we are applying a negative moment to the pre-stressed beam. Does it make sense to you? This process, that actually what we're doing here, we're just applying compression on the beam. So what's good about this? I mean, what did we gain when we have tension at the top, compression at the bottom? Just imagine now that I'm going to be taking this beam here and put it into service. This is going to be simply supported beam. Where is the service loads going to be coming from? Like the occupancy loads. We're going to say occupancy load is going to be coming like this. And all of this occupancy loads and service loads, they're going to be creating tension at the bottom, compression at the top. This means they're going to be counteracting the effect of this pre-stressing. In other words, this pre-stressing that you're doing here, the compression that you put on the bottom of the concrete beam, is counteracting the effect of this loading. Because look what happened. When I was talking here about design of conventional forced concrete, I said concrete is going to be failing once the strain is going to be approaching 0.03 on the top as a compression. Before you start the loading, I put some tension there. Now this tension means I have very low amount of strain on the top, and I may have also some tensile strain on the top in the concrete. So instead of putting only, let's say, 1 kip, now I'm going to be able to put 1 1/4 of a kip. Now I have more capacity here to add loads with having this pre-stressing at the bottom of the beam. Yes, Angel, this is correct.
Yep.
Tension is like adding a beam superpower. This is absolutely correct, superpower.
I also wanted to ask,
Yes.
does having epoxy coating on the tendons, does that like affect the efficiency of the bond between the concrete and the steel?
The epoxy coating, they don't do it to the tendons, they do it to the conventional rebar.
Oh, okay.
So the picture that you have seen,
They're coming
it
out.
was actually the connector or the connection between the beam and between the slab.
Okay.
Because think about it this way. In a double T, this is going to be just some concrete topping, right?
Mhm.
And in here, the roughness of the top of the double T should be enough, because this here does not support any flexure or any shear. This is only as a diaphragm. So it's kind of a little bit loose. It is not really possibly connected to the double T. But in bridges, it's going to be completely different. In bridges, let's say that you're going to see here a rebar, and the rebar is going to be coming like this, embedded inside the concrete beam itself. And then you're going to put here a concrete slab that you want it to be working as an integral part with the beam. So in a case like this, you need to put all of these dowels. It's going to be conventional rebars. And all of these conventional rebars and bridges usually
Exposed.
the epoxy coated.
Got it.
Yeah. So this is a little bit different from the strand. The strand usually, but yeah, generally speaking, once you do any epoxy coating, it's going to affect the bond a little bit. But in a case like this, bond is going to be okay, because actually the rebar is going to be bearing. It is not going to be really like intention.
Yeah. Yeah, I was under the impression that no matter what, if you're in an environment that requires that, then everything would be epoxy coated. But that makes sense.
No, but also you need to know that in post-tension, okay, when it comes to post-tension, I'm going to explain it to you, and also I'm going to emphasize on the sleeve and the tendon. It's going to be a little bit different from what you have seen here. So in the pre-tension, as you see here, there's going to be bond between the concrete and between the strand, and this bond is going to happen from day one. Once you put the concrete, when the concrete is going to start to harden, you're going to have this bond between the strand and the concrete. Now, once you cut it from both sides, the force is getting transferred. So we say here, this is going to be the time of transfer of the force. And this usually happens in 2-3 days after you cast the concrete. As they say here, the precursor says that usually we do it like in 12 hours. 12 hours mean that you need to provide maybe strong means for the hydration of the concrete, for the treatment, you know.
Yeah.
Now, the other method is called here post-tension. Post-tension usually happens in concrete slabs of buildings and in bridges. So what you do here, you cast the concrete first. And before you cast the concrete, you're going to put this hollow duct. We don't really call it duct, we call it a sleeve. You know the MC cables? Did you guys hear about it? Like electric cables, they call it MC cables. Yeah, yes or no? The MC cables usually they come like this helical. They have this sheeting, or you have this like cover, like a duct, if you like to call it, or a sleeve, and then you have the wires running inside it. Right? I don't know if you guys have seen this before, but if you work in construction, I'm sure that maybe you have seen it. They call it MC cables, right? So when you put the duct, you put it with the strand. So actually, when you buy the duct, it comes with a strand, and it comes greased from inside, so that it won't rust. And then you put the duct and the strand before you cast the concrete. You put it in place and you secure it. You anchor it very well to the form, and then after that, because you want it to take this drape or this shape, and then after that, you cast the concrete. After you cast the concrete, you're going to start to apply the tension, and this is what we call here post-tension. So it's going to be post-casting the concrete. The other one's going to be what you're doing here. You're doing pre-tension. Before you cast the concrete, you apply the tension to the cable. But here, you're going to be applying the tension to the cable after you cast the concrete. So in a case like this, you don't really have any bond between the concrete and between the cable at the beginning. Once you apply the force, look here what happened. You start here to apply the tension to one side of the cable. Of course, the other side is going to be anchored, right? So once you start to apply tension, it means that you're applying compression at the end of the beam, and this is what we call here the anchorage. It's going to be the strand anchorage. And then once you start to do this, now you have this tension on the beam, right? At this side, it means that you're lifting up the beam. This is exactly what you're doing. Once you start here to apply tension, this strand here wants to stay straight. It wants to do this. You see here what's happening? It wants to do this. It wants to stay straight. So it is pushing up the beam, which means it's counteract the effect of the conventional loading that later on you're going to be putting on the beam from the top. So you're going to give it here more service life, if you like, or give it more service capacity. So here's again the main difference. In the pre-tension, you put the tension first to the cable, and then you cast the concrete, and then you cut the cables from both sides. Now you transfer the force to the beam itself. In a case like this, you put the strands first, you cast the concrete, and then you apply tension to the cable. So in a case like this, you don't have bond at the beginning between the concrete and between the strand. And also the force that you have here is going to be applied at the end of the beam only. While the force that you apply here is going to be throughout the length of the cable because you have the bond. You see here the major difference? Here, the tension is going to be transferred to the beam throughout the entire length of the cable. And the reason because you have the bond from day one. When you cast the concrete, you have the bond between the strand and between the concrete. But in here, at the beginning, you didn't have any bond, right? So what you do here, as if you are applying all the force, is going to be at the end of the beam. Later on, in some construction, so this only in certain construction types, they have a mean to inject grout. So once you start here to inject grout, the grout is going to be going within the duct or the sleeve, and the strand is going to be filling in the gap between them, and it's going to be pushing the grease out. So once you push the grease out and you fill the entire duct or sleeve with grout, you're going to be preventing any colorides to come in touch with the strand. So it's going to be like a good protection to it. So it's going to be either grease inside, or it's going to be like grout, injected grout. It depends on the type of construction. Just, also pushing the grout here is not an easy job, and it's done certain projects, not any post-tension project. It's going to be in special projects. The good thing about the grout is going to provide also some anchorage, like bond between the cable, the strand, and between the concrete. So first between the cable and between the sleeve, and again the sleeve and the concrete is in one piece. And you need also to know that the sleeve also, it has this it has like a deformation, and the deformation here provides the anchorage between the concrete to the sleeve. When you have continuous beam, this is what you get. So here's a continuous beam, and you need to think here about the drape or the profile of the cable. The profile of the cable, if you go here with a straight, it means that you're pushing it up. This means if I bring this cable and put it here on the top of the beam, let's say that I have here's the beam. If I put the cable on the top, if I did here a mistake, what does it mean by that? It means that I put compression here at each end of the beam. This compression actually is not good, because this compression here, what it's doing, it's gonna be doing the same effect as the external applied load, the surface loads. You don't want to do this, because this is actually damaging the beam. This is not good. You'd like to put it right here at the bottom, at the tension location for simply supported beams. So when you have passive moment, you put the strands at the bottom. Here, when you have discontinuity, at this point you have passive moment, so I need the cable to be at the bottom. Here I have negative moment tension, it's given at the top, positive moment, cable is given at the bottom, and maybe at the end I'm gonna put it right in the middle. So we have a question here, says, does post-tensioning allow you to retension the tendons many years down the line after significant tension loss has occurred? And practically, not really. Especially in slabs, like building slabs, it's gonna be really tough to get in there and do any tensioning. I mean, it's not gonna happen. And in post-tension slabs, in many cases, we don't have the bond. But in big bridges, this could be important. But in big bridges, usually you have grout nozzle. So you have grout input, and usually inject the grout, because they are also looking for the bond. So, theoretically, yeah, this may happen, but practically it doesn't happen. Because how would you get into the slab? Let's say the 20th level, how would you get there? And do some tensioning? Yeah, I mean, you cannot. It's gonna be very expensive. It's kind of tough. I don't think so. I have a small video here about bridge girders.
Finally, you'll notice as well too, we've got shear link. Okay, now here is our typical stop end that would be used to orient the pre-stressing strands that we would use to apply that compressive force to the beam end. Now note, these strands are not tension, they're slack, so there's no danger here. You must be very, very careful with fully tensioned pre-stressing strands, because there's a massive amount of force that can be contained in each of these strands. This particular strand, in fact, we would actually tension up to a load of 209 kilonewtons in just one strand. So what we would do, these strands would be jacked up, they would be pulled back, and they would be essentially stretched. They would be put into that very large amount of tension, 209 kilonewtons for these. The concrete would be cast around the strands into the appropriate cross-section. Once that concrete has reached the specified strength, the specified compressive strength, then the strands would be gradually released, thereby transferring that force that was in the strands when they were stretched into the concrete. So that very large force in the strands would be then applied as compression into the beam itself. Now, notice that this strand layout is a far larger number of strands closer to the bottom of the beam. The bottom of the beam, the top of the beam would be just 50 mil underneath the actual bottom of the strand, 50 or 60 mil. The reason for that is not only do we want to apply compression to the beam, we also want to apply a bending moment to the beam as a result of the pre-stressing operation. So because that overall position of the strand is eccentric, it's removed from the centroid of the beam, that enables that application of pre-stress to also apply a bending moment that will counteract, will act against, and relieve the bending moment that results from the applied loads, the loads that will be applied to the beam under working conditions. Let's step back over to the finished beam itself and go through the final steps of the final aspects of how a pre-stress bridge beam works.
Now, quick question. Is this pre-tension or post-tension?
Pre-tension, because concrete poured after.
Because this is going to be in the fabricator's yard, right? This is in the factory, right? Okay. Would you have bond from day one between the concrete and the strands? I'm going to say yes, absolutely. Say, okay. Do you expect that this beam is going to be exposed to positive moment or negative moment?
Positive moment.
Why? Because look at this frame that I stopped at. 2.35, 2 minutes and 35, right? What's going to happen there? You have more strains at the bottom. So you want, when you apply the tension, it's going to be acting like this. It's going to be creating camber. It is pushing the beam up, so that when you put the loads later on, the service loads, you're going to put from the top, it's going to be taking it down.
Negative moment.
Yeah, so this here creating negative moment on the beam.
Beam is one of our finished products. This was actually cast not long ago on this bed itself. Now, you'll notice there's a bit of a gap between the soffit of the beam and the actual bed itself.
Why is this gap?
Is the beam deflected upward by the...
Yeah, it is cambered, right? It is pushing itself up. Just amazing. Once you cut the strands from each end, the beam was flat first at the beginning. It's going to do this. It's going to go up. Very similar to what we discussed here. If you give me a second, exactly what happened. Look what happened to the beam. You see this gap? It's going to be lifting up.
This is a result of what we just spoke about. When we apply that compressive force from the pre-stressing tendons, pre-stressing strands, not only do they apply that beneficial compressive force to the beam, but they also apply a moment that relieves the moment applied under working conditions. So this moment that's applied by the pre-stressing operation results in the beams actually cambering up. The beam will actually lift up several millimeters, 10 millimeters, whatever the case may be, depending upon the beam and the pre-stressing amount and layout used. It will actually camber up. Now, this is beneficial with regard to deflection checks as well too. Generally for bridge beam design, we don't need to carry out rigorous deflection checks, but from an aesthetic point of view, you don't want a beam visually sagging on site. So this natural camber that results from the pre-stressing operation itself will help eliminate the potential that that beam would be visibly sagging on site as well too. Finally, you'll notice as well too, we've got shear links in the beam as well. The shear links we use in the bridge beam would really be not substantially different from what would be you may be accustomed to for reinforced concrete bridge beam design too. So again, so bridge beam, pre-stressed concrete bridge beam would also make provision for shear design, shear reinforcement as well.
This reinforcing, in many cases, I have seen it to be epoxy coated. This makes sense to you guys.
So in order to summarize how pre-stressed, precast bridge beams work, beams are intended to carry flexure as well as shear, but that flexure that they're going to carry results in tension in one face of the beam. Concrete is not good in tension. In reinforced concrete, we use bars, steel bars, but in pre-stressed concrete design, we apply compression in order to overcome that tensile stress in the beam due to flexure. The force is applied using pre-stressing strands. Pre-stressing strands are stretched. Concrete is cast around the strands in pre-tension concrete, and the strands are slowly released, thereby applying that compressive force to the beam while simultaneously applying a moment to the beam that also acts to relieve the applied moment. I should also point out as well too that what I've been speaking about here relates to pre-tension, precast, pre-stress bridge beam design. There is also post-tension bridge beams, which are slightly different, well, rather different from pre-tension bridge beam design.
Right, any questions? Any comments? All right.
Do they check the uplift, or do they just go?
The camber. Yeah, the camber, absolutely. Especially when it comes to final deflection analysis,
Mm-hmm.
this camber is gonna be subtracted from the total deflection.
Mm.
So this is what's also good about pre-stressed beams that you have this camber, right?
Yeah.
So it's gonna save you a little bit of the deflection. So where can we use pre-stressed concrete? We say bridges, we say buildings, hotels, big tanks, and so forth. What is a good thing about precast? What's the better advantages? I'd like to hear from you guys. I guess we have tried there. Now, consider that you take the beam and then you put pressure on both ends. What's going to be the result of doing this?
Basically, it's going to put any neutral section in compression, and it's going to reduce the tension on any section that's already in tension.
Right. It's going to reduce the cracks. And actually, in pre-stressed members, I can do a member which is going to be 100% free of cracks. This is why it is very good when it comes to water tanks. Because in a water tank, if you think about using conventional concrete, you're going to say, well, concrete is going to crack in the tension side of the steel. It's going to be a big problem, so I need to waterproof it. In a case like this, I can have it to be watertight. No water at all. I can have it crack-free. This can happen. If I have this corrosive environment, why is this going to be better in corrosive environment? Because you're going to be reducing or controlling the cracks. So in a case like this, no moisture, nothing's going to be getting into the rebars or the strands. That's why it's going to be corrosive. It's going to be better in corrosive environment. Now we were just talking about the camber. So what is the result of having camber when you're doing deflection analysis? Now deflection is controlled. I'm just reading here. I'm just taking an item by item. I'm trying to relate this to our discussion. So here deflection is going to be controlled. Why? Because of camber. Diagonal tension is reduced. This gives you something about the shear strength. Just imagine here, what creates the shear strength in beams? You're going to say rebars. You're going to say yes. How about the concrete? You're going to say yes, absolutely. Concrete resists shear. It has a value. If you remember, it's going to be equal to 2 square root of A prime C. That was the equation we used to use. What does this do? Do what? I mean, what's causing it physically? I'm going to say the interlocking between the aggregate, right? So, for example, if I give you here a section, it's going to be 100% exposed to tension, concrete section. It has some rebars. Now, think about any shear friction resistance. Would you have any if the section is going to be under tension? It's going to be nothing, right? Because when you apply tension, you open the interlocking between the aggregate particles and the cement. Now, think about putting compression on a member. You put compression, you increase the interlocking between the particles and between the aggregate, and you increase the shear strength. So actually, it's going to be stronger than shear. And the equation of 2 square root of A prime C is going to be modified because I need to add a factor for the compression on both sides of the beam. Is it less construction time? I'm going to say yes. It's going to be like structural steel. You carry the member, you put it in place, you're done. There is no formwork, right? You don't have any formwork. It's kind of heavy members to transfer when you compare it to the steel, but it takes less time. What else? You're going to be working here with high strength materials, right? Concrete's usual strength is going to be high, the strength is going to be 270. And then you can also do the testing of materials, right? Where do you make it? Right there, you can test the materials. Shear in concrete reduced for certain profiles. We're going to be talking about this. Economy due to reduced member size. So the member size itself is going to be lighter because the depth is going to be shallower. So when it comes to the seismic force determination, it's going to be just much less. You know, the seismic force is going to be related to the weight of the building. And here you're reducing the weight of the building by a lot. You can work with larger spans, yes. What is bad about it? What is bad about it? You're going to be doing lots of analysis. Something that you don't like as an engineer. But you know what? When you practice, you're going to have a software. This is going to be the good thing about engineering, right? We don't really do everything by hand when it comes to analysis. But generally speaking, you need to watch for the stresses. In conventional concrete, once you do the strength design, which means that you provide capacity more than demand, you're done. Member design is complete. In here, the surface stresses, and then you're going to have phases. You're going to have during construction, which means during the cast, at the time of transfer, and then after you apply dead load, after you apply all the service loads, you're going to have more than one stage at which that you need to calculate out the stresses and be sure that you're not exceeding it, whether it's going to be in tension or compression. So the analysis is going to be a little bit complicated. You cannot come up with your own size, right? You guys, you understand that. The member size is not going to be that flexible. When you do conventional concrete, you can play with it. Also, the shrinkage. You need to consider the shrinkage of the concrete and the aggregate. Why? Because of the losses. The pre-stress losses is going to be a big deal. And the type of material that you use is going to be affecting the shrinkage. You don't have this problem in conventional concrete. So the losses is going to be another thing that you need to look at. Here's a simply supported beam. Now I'm trying here to compare the performance of conventional concrete beam with pre-stress beams. Typical load is going to come from the top. So what you do here, you put the beam, you build it, you put the rebars inside it, and then you cast it, and then you start to apply loads. What's going to happen? Bottom of the beam is going to start to crack this way. So, all right, I understand that. This is simple and easy. So what happened here in pre-stress? In pre-stress beams, at the beginning, you put the cable, and then you put the concrete, and under its own weight, under the self-weight only, you're going to see here some camber. You can control this by design. You do the camber, the amount of camber is going to be equivalent to the dead load deflection. So here, once you put the dead load, the beam is going to be flat, which means by calculation here, deflection due to dead load is going to be the same as a camber. We'll come to analysis. So the good thing about this, because you know in bridges, the amount of live load is almost nothing. It's very small. It's just negligible. But the amount of deflection due to dead load is going to be the controlling factor. So if you like to have a clean beam, it's going to be kind of a straight beam, no deflection, no camber, nothing. You just do your analysis and you set the camber to be equal to the dead load deflection. And that's it. Live load is just ignored because live load is going to be just the cars. And the weight of the cars compared to the weight of the bridge is almost nothing. It's very small. So what happened in beams, we actually put conventional reinforcing like this blue, you know, the light blue. And then we put also cables in the same time. We put the tendons and also put the conventional rebars. So that at the beginning, when we add the dead load, what's going to happen? The beam is going to be straight. And then after you put the service loads, you're going to see here some cracks. And this is going to be like the optimize. If you like here to optimize your design, you add the strands and at the same time you add this conventional rebars. But this amount of conventional rebars is not going to be that much. It's going to be very limited amount. Let's say in a beam, you're going to put, let's say number 6, you're going to put maybe 4 number 6 or 6 number 6, compared to the same beam that you had put maybe 12 number 8. So you don't really put lots of rebars, but you put some rebars to control your design and to optimize it. I guess I'm going to stop here at this point. Now this is going to be coming here to analysis of pre-stressed beams. And I let you go at this point. And you guys, you remember that next time is going to be in class, right? It's going to be in person. All right. Give me a second here. I'm going to show you, because I remember I've seen it today. I'm going to show you the MC cable. Give me a second. It seems that someone moved it. I'll be sure to bring a piece to the lecture. All right, guys. You have a good night. And
Thank you.
yeah, please go ahead and sign out.